pressure now. Maggie, don't worry. See, I already got Maggie already on video. Okay, so the bonding continuum, polar bonds, and don't worry about that big comment there. And again, the only reason I'm kind of bringing this up, and let me just bring this whole thing up here. Here we go, like that. And you'll notice I've left you a space in the middle. You can write that stuff down. And I've left that space in the middle on purpose. So we finished drawing our Lewis diagrams of the not so nice, all right, who's kidding who, they're ugly, of the ugly structures yesterday. And you might think, hey, that's it, we've got it. We know how to deal with ionic compounds. They trade their electrons and they form ionic bonds. And we've now dealt with covalent or molecular compounds. That's easy. They share their electrons. We know it's not really sharing, it's more of a tug of war. And you might think that's it. We've mastered the compounds. We're done. But unfortunately, when it comes to the sharing isn't always equal. And that's what we want to talk about for today and tomorrow. What happens when the sharing of the electrons is not equal? And how do we describe it? And what does this mean for the properties of the materials? That's really kind of where we're heading. Because in the end, all of this that we've been doing is theory. It's the theory that involves sharing of electrons, pairs of electrons getting together. And ultimately, we want our theory to be able to make predictions to what we see in reality. And so what we're going to do now is we're going to learn about the way different atoms share, and then tomorrow we're going to talk about how that then equates into what we see. So here are the two types of sharing that we've encountered. Ionic, a complete transfer from a metal atom to a non-metal atom, producing oppositely charged ions. They stick together, it repeats, it makes this lattice structure that's really strong, and we have an ionic compound. And we've just dealt with the covalent bonds, equal sharing between non-metal atoms. And you'll notice I've added a couple of extra words there, non-polar. And that's because the third type that we can have is this type that is in between. It's not equal sharing, and it's not a complete transfer, it's unequal sharing. And when we have this unequal sharing, we end up with a polarization of the bond. And therefore, we call it a polar covalent bond. I'll explain why it's called polar in a moment. Right now, you're probably imagining the North and South Pole of the world with some bears and perhaps some penguins and Santa Claus. But that is not what we're talking about. It does have to do with opposite ends. There's the only similarity between that. We do have poles on the Earth, opposite ends of the Earth where the axis of rotation is, and these bonds have distinct opposite ends. That's why it's called polar. But again, I will describe that in a moment. So there we've got our types of bonding. So let's now investigate a little bit about what is meant by having a polar covalent bond. Again, I am now reminding you, reintroducing you to the term electronegativity. I brought it up yesterday a little bit. Yep.
Why is there a triangle in front of the EN?
That triangle is a Greek letter, and it is, that's nice. Peter wants to be on the video. That's great. That's good. That's why he did that. That's fun. I'm going to go back and see if you can hear him. That triangle is a Greek letter. It is a capital delta. And are you taking physics, Peter? Oh, okay. we cannot do this. We cannot do this all class long, and we'll never get done. Okay, that capital delta, it stands for difference. All right, difference in the electronegativity. All right, so in physics you will learn that there's an equation. If you want to determine the velocity of something, you can write it down as being delta D over delta T, and that symbol delta represents a difference, so a subtraction, and it means typically D2, the final position, minus the initial position, and then the delta T would be T2, the final time over the initial time. In this case, it simply means difference in electronegativity, how different those numbers are. Now, having said that, we are going to need to be able to know our electronegativities, which means we are going to need our periodic tables. And we know how that always goes. I'll leave it out there for those who need it. Actually, I'm going to deliver it to the left, my left side of the room, because I don't want you guys bumping the cart. Because if you bump the cart, then I'm not organized. Do you need one of these? Yeah. Who needs one? Oh my goodness! I should be naming and humiliating you all on over the world. Trust me, if you want to be entertained, you just need to watch some of my others. I make fun of all kinds of people. I make fun of people from like 5 years ago and 6 years ago. What's that? I didn't record any for him. I didn't record any new ones. Okay, let's just pretend I'm not recording. Let's just be natural. You guys are killing me here. How can I help you? Okay, so it is the difference in the electronegativity of the bonding atoms that results in the different types of bonds. The greater the delta En, that's the way I'm going to say it, delta En, but it just means difference in the electronegativity, the more ionic the bond is. The smaller the delta En, the more equal the sharing of the pair of electrons, and the more covalent it is. All right, and I'm going to put some examples up, obviously, to describe this. At this point, you're just seeing delta En and some other terms in there, ionic and covalent. So in a moment, I'm going to do a couple of examples to show you what I mean by this. Okay, are we good to go? We're good to go? No? No? Yep. The triangle? I will never ask you to explain what a delta is. No. But I will talk in terms of delta En, and you may want to use that term in your explanation. So if I ask you to maybe compare a couple of bonds that we're dealing with, you're going to maybe want to talk about the delta En. And all you need to know is that it means the difference in the electronegativity numbers for those atoms. All right? But I'll never make you define a delta, you know, that type of thing. Okay. All right, let's do some examples here. Don't write down the bottom part at this point. So let's take a look at HCl. So I'm simply going to draw the Lewis structure for ACl or HCl to begin with. So I've got my hydrogen, and by the way, this is a nice structure. So we've got hydrogen, typically has one bond. We've got our chlorine, typically has one bond and 3 lone pairs. So we're going to draw that up, and we're going to result in this structure, which is nice. All right? And now we're going to analyze the electronegativities for both of those. I typically do the calculations right below them. So I'm going to write down here delta En equals. And now I'm going to go to my table, and I'm going to find the electronegativities for each of the atoms. So if we take a look at our periodic table, and we use the legend there, I believe you'll notice that the number to the right of the symbol, directly right of the symbol, is the electronegativity value. So if someone could tell me, other than Peter, the electronegativity value for hydrogen, that would be helpful. What is the electronegativity for hydrogen? Yeah, Haley? 2.2. 2.2 minus, because it's a difference. That's what the delta stands for. And what's the electronegativity, Riley, what do you got? 3.16. And now I need you to get your calculators out and do a quick little calculation to tell me what the difference is. Now, it turns out that I'm not interested in the sign. So if we do a calculation and I'm not interested in the sign, in mathematics we put these bars around here. They're called absolute value bars, and it means just don't bother telling me what the sign is. Kayla, do you have a number? 0.96. 0.96. So you can see there that there's a difference in the electronegativity of 0.96. And you can see here that the chlorine's electronegativity is greater. Remember, the electronegativity is the ability for an atom to pull electrons towards it. So what does that mean? That means that this pair of electrons in the bond doesn't actually exist right in between the two atoms. This pair of electrons actually exists a little closer to the chlorine because the chlorine has a greater electronegativity. The way we represent this fact that this pair of electrons exists closer to the chlorine is we use a special arrow that we draw close to the bond and points towards the chlorine. And on the back end of that arrow, we don't put like feathers for like an arrow, but we actually put a little plus sign. So I put a little line to make the back end of the arrow plus. Now the reason we do that is if the electrons are existing a little closer to the chlorine than to the hydrogen, it means the chlorine is taking the electron away from the hydrogen. If a hydrogen were to lose its electron completely, let's say something pulled really hard on that electron and took the electron away from the hydrogen, what charge would the hydrogen become if it lost its electron? What charge does the hydrogen become? +1. But this hydrogen isn't losing its electron completely. It's just losing it a little bit. So it's not that there's a +1 charge on the hydrogen, but there's a plus maybe half a charge or a +0.2 charge. But there's a little bit of a plus charge. So the way we represent this tiny little bit of a plus charge is using a symbol that looks like this. Now, you might say, what the heck is that? That is also a delta, except it's a little delta. The Greek alphabet has capital letters, just like it has lowercase letters, just like us. And in Greek, the capital delta is a triangle, just like we have a capital D. Lowercase delta looks like this, and I imagine it as if it's a number 8 that I really just didn't want to quite finish. That I got a little lazy, came around the corner and said, yeah, I'm not going to finish that 8. I'm going to leave it right like that. Notice, if you imagine, you might be able to see that it looks a little bit like a D. Yeah, maybe. All right. So what does this little delta mean? This little delta with a plus means that it's not +1, but it's just a little bit of a plus. It's a slightly positive charge. Not completely positive, but a little positive. So when the electron shifts towards the chlorine, that makes this slightly negative, because it's got a little extra electron closer to it. So what we've got here is we've got a molecule that has now 2 distinct ends when it comes to charges. And that little molecule that has 2 distinct ends will behave just like, you go ahead, will behave just like this little thing right here in my hand. What is this? It's a magnet. What do magnets have on each end? Really? Julia? What do we call the ends of a magnet? No? Poles! Woohoo! I was a little worried there for a moment there. Poles. Poles. Whew. They have two different poles. We could say that this magnet is polarized. It has two different distinct ends. Just like the Earth has two different distinct poles, the north and the south, the Earth is polarized. It actually has magnetic poles as well. This molecule has two distinct ends, and therefore we say that this molecule is polarized. It's a polar molecule because of this electron being shifted slightly closer to the chlorine. Question?
What's the point in drawing the little plus sign and the arrow closer to the hydrogen if we're just going to say that it's positive with the little delta sign anyway?
Okay. Both of those insignias that I've put up there, the arrow with the plus sign and the deltas, it is redundant. They both mean the same thing. Both of those things represent what we call dipoles. So you could put the arrow with the plus to represent the fact that the H is plus and the direction of the electrons moving, or you could put the little delta negative and the delta plus, and they mean the same thing. They mean that there's two distinct ends to the molecule. Yes?
So we don't have to both.
No. If I ask you to draw dipoles, you can use whichever form you'd like, but they both appear in textbooks. Yep?
Would you like us to write?
Yes. At this point, I want you to write the definition of what a dipole is. All right? But I first had to draw it, right? That's what I was trying to explain to you, what a dipole is. Now, I went online to find the actual definition of a dipole because I've never really thought about it. I just kind of assumed I knew it. But when it came to writing the definition, I really was thinking, what do I really need to have in that definition? They provided me with an equation, and I didn't want to get you guys all caught up in equations. We just want to have a feel for what this dipole is. So it is a value. There is a number that is associated with this dipole. It's a calculatable thing. But I want you to think of it as an arrow or the distinct ends. It's a value that depends on how far apart charges are and how big that charge is. Don't worry about how far apart they're moving or how big the charge is. I just put that definition there so that you had a feeling for that it's something that we can calculate. The only thing I need you to worry about is the greater the delta En, the bigger the difference in those ENs, the bigger the dipole is, because it means that the electrons shift more. It results in a greater distance, or how far apart they've been shifted, and it also results in a bigger charge that's being moved. Okay? You just need to know that the delta En affects that. All right? Let's do one other example. Let's do an H bonded with a P. Now, that phosphorus, if we draw it upright, will actually be bonded to 3 other P's. And notice how I drew them smaller and out of the way. I'm just talking now about the bond. I'm not talking about the whole molecule. I'm just analyzing whether a bond is polar. The second half of this lesson will be looking at whether the whole molecule is polar. So at this point, I'm just analyzing the delta En for the H and the P in that bond. So En for H, we've just used that. Now I need an En for the atom phosphorus. Yep, Haley, what do you got? 2.19, 2.19. I don't care about the sign that comes out of the computer. What number do you got there, Michaela? 0.01. And look at that difference in electronegativity. How would you describe that number? Peter?
Extremely small.
Extremely small. That means this is practically equal sharing. The electrons are hardly shifted. We actually wouldn't even draw an arrow to represent that. We would say here that there is no dipole. All right? There's no dipole. Yep. My next slide is going to tell you exactly the numbers we use. Okay? So that's a good question. How do you decide whether there's no dipole or whether there is a dipole? Well, chemists have decided that. They've decided by looking at the properties of the materials, they can have an idea on whether there's a dipole in there or not a dipole. So how do we decide? We decide with what is called the bonding continuum. All right, there it is right there, and I'm just going to back that off right there and let you write that down. So chemists have decided that if the delta En is between 0 and 0.2, that is small enough, and they would say no dipole, no arrow needed. That's not enough shifting. If it's between 0.2 and 1.7, if it's between 0.2, if it's between 0.2 and 1.7, we say that it is polar. We would draw dipoles in there. And if it's greater than 1.7, we say that the electrons have shifted so much that it's become a complete transfer, and we say that that is ionic. So the reason this is called a continuum, well, we've already encountered a continuum in this class. We encountered the continuous spectrum. What was the continuous visible spectrum? What's the layman's term for a continuous visible spectrum? Oh my, look at that continuous visible spectrum. Isn't it beautiful? Yep, a rainbow. The reason it's called a continuum is because there's no breaks in it. It goes continuously from red, orange, yellow to green, blue, indigo, violet, and there's no breaks. It's got this kind of change in color that you can't perceive. It turns out that the bonding of molecules are exactly the same way. We've been teaching you for years, ionic compounds, metal and nonmetal, covalent compounds, two nonmetals, that's it. Put them in that pile or that pile, you're done. But we now know that that's not the case. We actually have perfect equal sharing. We call that pure. And then we've got, a little bit of unequal sharing, but it's not too bad. We'll still say that that's nonpolar. And then we've got, unequal sharing that's just on the high side of 0.2. All right, that's polar. But something that's at around 0.9 is more polar than that. And something that's at like 0.6 is really polar. And then we say, well, when it gets to 0.7, it's so polar, we're going to say that it's traded and it's ionic. But then if you get even higher than that, is it more ionic? Well, then it's even more pulled to the one side. So it's a continuum depending on what the numbers are. All right? Now, like I said, these numbers are just kind of picked by scientists. This number right here, the 0.2, I have found literature that says 0.5. My 4U textbook says 0.5. Your textbook says 0.2. I did some searching online. I've found various versions. Depending on which chemist or which group of chemists you're talking to, they support one versus the other. Because it has to do with the way those particular compounds behave. Don't stress about it. We're using 0.2 as the dividing line. Okay? Don't stress. All right, let's quickly do some examples here. So, H2. I'm just going to draw the little structure here. Delta En. Well, we could put the numbers in, but if the atoms are the same, what's the delta going to be? It's going to be 0. It's going to be 2.2 minus 2.2. 0. We would say that that's pure. That's a pure covalent bond. That is equal sharing. HCl, we've already done this. We did it in our last example, so I'm going to just quickly write it down. I'm not even going to draw the picture. Delta En, I believe it was 0.96. Was it on our last slide? That's correct. 96? 96. So you can see there that it exists in that region between 0.2 and 1.7. That is a polar covalent bond. We would draw a dipole on that. Okay? NaCl. I'm not going to draw the structure for this. I am going to do it in a moment. So let's just do the delta En first, and then I'll draw the structure underneath it. So I need the Na and I need the Cl values. Peter, what do you got? Okay. Tim?
Chlorine is 3.16.
Oh, my Lord. I shouldn't have said anything. Tim, what do you got?
2.2.
2.2. Well, thank you, Tim. You can see there it sits in the ionic. So I wouldn't actually draw this like a molecule. It would be incorrect for me to draw a single bond between the sodium and the chlorine. So if it's ionic, we already know how to deal with it. It means that the sodium has given up its electron and has become fully a +1 charge. The chloride or the chlorine has gained its electron and become a -1 charge. So because it's ionic, we would represent it that way. Yes?
Wouldn't delta En be 0.23?
Is it 2.23? Just trying to show them up. Is that what's happening here? Okay. Are we okay with the idea that the delta En is greater than 1.7, therefore it's ionic? So, H2 is a molecule, it's molecular. HCl is also a molecule, but it's polar. It has a dipole. We saw that on the last slide. But NaCl is ionic because its delta En is so great, and we draw it as if it's an ionic substance. Okay, let's do a couple of examples of some problems here. Two molecules there. Which has the larger dipole? Is that a question, Peter?
No, it's an answer.
Well, we don't want that yet. Essentially, down to the simplest kind of level, what am I doing in order to determine this situation? Peter, just give a rest, man. Give it a rest. Go on to the next slide. Do the next question. Don't go too far though, because then I'm going to deviate from the PowerPoint. What do I have to do to find this? What am I ultimately trying to find if I want to figure out which has the largest dipole? What is it that determines how big that dipole is? What am I doing? I need to calculate the delta En for both of them. Then what am I going to do? How am I going to tell which one then has the largest dipole once I've calculated it? What do we know about the delta En and the dipoles? It's in our note. If you go back and take a look at the definition on dipoles. What do you got? Madison, what do you got? We've calculated the delta En. Now, how are you going to tell? Whichever one is larger is going to be the biggest dipole. So let's do that. Delta En for HCl. Well, guess what? We've done that to death, so we don't need to do that. 0.96, I believe. Delta En for HBr is going to be, I believe, 2.2 minus. Michaela, what do you got? 2.96. And so what is that value? Have you calculated it, Michaela? 0.76. So which one has the larger dipole? Madison? HCl. Therefore, HCl has larger dipole. All right? In the picture, we could represent it with a little longer arrow. Okay? Which is the most polar out of those two. Which is the most polar? Which is the most polar out of those two molecules? Which one is the most polar? Yeah, what do you got there, Lauren? And why is that? Because the delta En is bigger. Asking which one is more polar and which one has the largest dipole, it's the same question. Those are asking the same thing. So HCl has the larger dipole, therefore is more polar. Okay? One last example. Rank from least ionic to most ionic. Notice how I've used the term ionic, but it doesn't matter. It's a bonding type. How could we, what other term could I use to say least ionic? What would be the farthest away from being ionic in the bonding continuum? What is least ionic? Yep, nonpolar. So in the end, I'm asking you to rank from nonpolar to polar, to the most polar, to the most ionic. So again, we're looking for delta En. I'm just looking for the bonds themselves. So notice we've already dealt with pH3. We only care about the P and the H bond, or the H and the P bond. I don't care about the fact that there's three. That means there's three bonds in there, but I'm only looking at the bond. Does anybody remember what the value was for pH3? When we did the pH bond, what was the value of that delta En? 0.01. We've already done an HCl, 0.96. I'll take the numbers when they come in. As you're calculating, I'll take some of them when you, Michaela, what do you got? For this one, 1.78. Anybody got any others if they're coming in? Again, when you get it, I'll take it. Yep. 3.0. 3.0. Yep.
For CS is 0.03.
0.03. Not very polar, that's for sure. Yep. We're crowdsourcing this one. Yep, Michaela, you got one? 1.24. Gee, I want to think that that's a little higher. Do we like that one? It could be. I just can't remember. I haven't calculated that. We like 1.24? Okay, that's good. And the last one?
CH4 is 0.35.
0.35. So we're going from least ionic, least to most ionic. Which is the least ionic? Yep. pH3. We're going to now rank it from smallest delta En to greatest delta En. In my note here, I'm just going to put a delta En here on the bottom so that you can see that those are all delta En numbers. So what am I doing? pH3. Then what? CS2. CS2. CH4. CH4. HCl. H2O. HF. And LIF. Okay? Right? That's just a table of electronegativities that we used to use on the other periodic table, but you guys are finding them there. Okay, so that deals with polarity of bonds. There's a few questions out of the textbook that you can do, but I'm going to keep going because now I want to talk about the entire molecule. Because I'm sure I've brought this out before. Have I shown you this thing before? Yeah, talking about the tetrahedron. This is the actual shape. If I had a white molecule or atom on the end of this, this would be the actual shape of the CH4. And each of these bonds would have little dipoles on them. And the question is, how does the shape affect the polarity of the whole molecule. So now we want to talk about the entire molecule itself. How does the molecule behave? Now, at this point, I'm going to end up getting myself into trouble, but I'm going to do it, because I'm going to deviate from this, and I'm going to write the note on the notebook, and I'm deviating from my note because the note, I think, is a little confusing. I'm going to try something new. Yep.
It's gonna be like,
I have no idea. I have no idea how long this is going to take. So this is, whoops, don't want yellow. This is polar versus non-polar molecules. So notice at this point, I'm not talking about bonds, I'm talking about molecules. The first thing we need to learn, the first thing that's important here is how two dipoles can interact with each other. All right? So now we're going to talk about a molecule that has more than one bond, which means they're going to have more than one dipole. So let's talk about what happens when dipoles get together. Dipoles can add to each other or cancel each other out. So dipoles can add together, or they can result in canceling each other out. So let's say then that I've got two dipoles, and they're not even part of a molecule right now. We can imagine them as being two separate magnets. So here I've got two magnets, and you can imagine that I attach the magnets to the bonds, and I bring those magnets really close together. And when you bring magnets really close together, their magnetic fields interact. And that's what happens to dipoles. So I could have a dipole that's going this way, like that. It's on a bond. But if I have another bond that's nearby, that dipole could go that way in the opposite direction. And those two dipoles would cancel out. In the end, no dipole. They canceled. Canceled out. All right? So dipoles that are going in opposite directions will cancel each other out. They'll just completely negate each other. They're like opposite charges. It's like it becomes neutral. Yep.
That only works if they are, like if you have a dipole like a zero.
Correct. They would need to be exactly the same size dipoles. Correct. If they were slightly different, then you're right. They wouldn't cancel out. So if I had a long one going one direction and a short one going the other direction, it wouldn't have canceled out completely. Correct. They've got to be the same size. Okay. If I had, well, let's do that as an example. Let's say, oh, I wanted that to be red. Let's say I had one going this way, and then the other one going like this. That's not in my note, but I like that idea. Okay? So one goes that way. It's really big dipole, but the other one is a smaller dipole. In the end, you end up with this little bit being left. All right? So in other words, does not cancel out. That little piece was left. That's why I put it as a different color. So in this case, it did not cancel out. Actually, you know what? This is where I get into trouble. I've got that arrow going backwards. I don't know if I can erase. I've got that arrow going, oh, I can move it. That's not what I want. I want to erase it. Oh my goodness. Oh my goodness. This is not really fun. Okay. Okay, let's just dismantle it. No, I'm just going to dismantle it. In the end, notice how the one going to the right is bigger. That means we have a dipole that's a little bit left that goes to the right, right? It's still going to the right. So I had the arrow going the wrong way. The big one is dominating. So in other words, does not cancel. Does not cancel. All right? I can also have the same if they're on an angle. I could have one going this way, and I could have one going that way. and those don't cancel. It actually will result in one that kind of cuts across there, okay, because they add. So in the end, what do you get there? You're going to get something like this, okay? Again, does not cancel. Does not cancel. So they can cancel if they're the same size and going in opposite directions, all right? If you've ever taken anything in physics or math called vectors, this is what vector addition is. But you guys, I don't think of as taking anything on vectors, so you don't know yet. But it's really just that simple. Okay. Let's keep rolling on. I'm going to move down here. I'm going to extend the page, so hopefully you can still see. All right. So, and again, I just wrote this earlier on. If a molecule has dipoles, oh, I've screwed this up, but that's okay. If a molecule has dipoles, sometimes, I wanted to put sometimes. Sometimes they can cancel. If they do, the molecule is non-polar. Oops, non-polar. Right? So if a molecule has dipoles, sometimes they can cancel out, and if they do, the molecule is non-polar. Let me give you an example of it first, then I'll take your question. Example, CO2. Looks like this. And has lone pairs on the O. Let's do the delta En. En for O and En for C. Yeah, Tim?
3.44.
Yep.
And for C,
Sorry? 2.55. 2.55. So, what is that? Yeah, Michaela? Is this bond polar? Check your range. What range of numbers do we need for polar bonds? You need to check your bonding continuum. So is this polar, Michaela? Yes, it's between 0.2 and 1.7. Which way would the arrow be pointing? Which way is the arrow pointing if I were to draw my dipole on this carbon and oxygen? Which way is it going to point? Yep. Out to the oxygen, the higher electronegativity. So it's going to go this way, and it's going to go this way. Notice those dipoles. They're exactly the same size, and they're pointing in opposite directions. I know that it doesn't look like they're right on top of each other, but the molecule is phenomenally small. It's super small. It's a small, tiny thing. So in essence, they're really right on top of each other because it's such a tiny thing. These dipoles cancel. In this case, we have polar bonds, but the dipoles cancel because they're going in opposite directions. And therefore, this is a non-polar molecule. This molecule is not polar because the dipoles cancel out. Okay? if the dipoles do not cancel out, so if we have a situation where they're not going in opposite directions and they do not cancel out, then the molecule is polar. We say it's a polar molecule. The example I'm going to use there is H2O. So H2O, again, it's a nice one. Hopefully we can draw it. 2 lone pairs and 2 lines, right? It's in group 6 from all that stuff we've been drawing. Dot, 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 H, H. We've already calculated the delta En for H2O, or the delta En for an H and an O. I believe it was 1.24 when we did that question at the very end of the last thing. 1.24. 1.24. So what does that tell me about the bonds in here? The delta En tells me just about the bonds, not about the molecule, but just about the bonds. What's true about that HO bond from that electronegativity? Yep, it's polar because it's in between 0.2 and 1.7. Therefore, we have polar bonds. The oxygen has the bigger electronegativity, so the arrows will point towards the oxygen. And if you take a look at that shape, will those 2 dipoles cancel each other out? No, they're not going in opposite directions. In this case, the dipoles don't cancel out. Now, the reason they don't cancel out is because this molecule isn't symmetrical. It bends in one direction. And so the reason they don't cancel out is because the molecule is non-symmetrical. We have a non-symmetrical molecule. Therefore, the dipoles do not cancel. And therefore, it is a polar molecule. This entire molecule is polar. All right, it will have a positive end and a negative end. Yep, question? What do you mean, why can't I make it symmetrical? Right, so you mean put it on the opposite side and just create it to be symmetrical. Is that what you're saying? Okay. These molecules are all actually 3-dimensional shapes. And I haven't taught you how to determine the 3-dimensional shape yet. So there's no way for you to know whether it's symmetrical or not. This molecule of water is exactly the same as this molecule here that I was showing you earlier on, except I'm going to take these away. And you can imagine that the holes are the lone pairs. Okay, see I got a hole there and a hole there? If I were to hold this in line with your face just like that, you'd say, that's a line. That looks symmetrical, doesn't it? But as soon as I turn the molecule like that, you'll notice it bends down. You see what I'm talking about? That is non-symmetrical. And the reason it's non-symmetrical is because of the lone pairs themselves. I don't have enough time in this course to teach you how to determine the actual shape of this molecule, which, by the way, is called bent. We call that a bent molecule. So I'm going to teach you a shortcut to figure out whether it's symmetrical or not. If the atom in the center has lone pairs on it, those lone pairs push the bonds to be non-symmetrical. Notice in carbon dioxide, notice, does not have any lone pairs. See how there's no lone pairs on that carbon? If there's no lone pairs on the central atom, it turns out that the atom is symmetrical, and the dipoles will cancel out every time. If there are lone pairs on the central atom, it breaks the symmetry. It pushes the bonds out of the way. So if there are lone pairs, then it becomes non-symmetrical. So we're really looking to see whether there's lone pairs on the central atom or not. And that's what my last part of my note is here that'll allow you to do this completely. So how do you know whether it's going to be symmetrical or not? It has everything to do with lone pairs. And that's where my next thing is. So that was a good question because that's a legitimate thing. So let me get rid of this. So, oops, that's not right. I need that. How to tell, really we want to know whether it's symmetrical or not, but I'm going to write in here how to tell if the molecule is polar. So now I'm going to put that all together. There's a question right there for y'all. Or you can put it as a title. I don't care how you do this. Now, in the past, I've done this with a big flow chart, and I've had slides upon slides, and it's really quite chaotic. But I've tried to break it down into 3 rules that you can follow to determine whether that is. I've tried to simplify it. By the way, I've done this all because I knew you'd be asking me questions forever, so that's why I've changed this today. Number 1. If there are no polar bonds, so let's say we do the delta En, and the delta En for all the bonds is small. There's no polar bonds. It's less than 0.02. If no polar bonds, and what does that mean? It means the delta En is in between 0 and 0.2. Notice how I put an arrow there instead of a line because I didn't want to confuse it for a subtraction. We're not subtracting. That's your non-polar scenario, right? If it's between there, then you can stop doing the problem because if there's no polar bonds, there's no dipoles, and it's a non-polar molecule. Doesn't matter what you're dealing with. You've got to have the polar bonds in order to have it. So if there's no polar bonds, therefore it's a non-polar molecule. You're done. So do the delta En first. If there's no polar bonds, you're done. It's a non-polar molecule. 2, if you have polar bonds, so if yes, oh my goodness, yes, polar bonds, you then need to see whether it's symmetrical or not. So if yes, polar bonds, you need to now go to the next kind of step. And the next thing you need to ask is, are there lone pairs? So if yes, polar bonds, and there are no lone pairs on the central atom, on central, if there are no lone pairs, PRS, on the central atom, so there's no lone pairs, then we have a symmetrical molecule, symmetrical, and I apologize for my big writing. I wanted this to run right along the page. I have to go like down around the corner now and head back. If it's symmetrical, the dipoles cancel, just like we saw with carbon dioxide. And if the dipoles cancel, you can then say, therefore, it is a non-polar molecule. All right? So if you've got polar bonds, you look at the central atom, check for lone pairs. If there's no lone pairs, it's symmetrical, and they cancel out, and it's a non-polar molecule. And again, you're back to non-polar. Number 3, if yes, polar bonds, you move on to the next. Now we're saying yes, lone pairs. there's actually a second way that you can have non-symmetrical situation. You can have different atoms on it. So the atoms could be different. Like instead of H and H, you got an H and a Cl on the other side. If yes, lone pairs or different atoms, then again, we now have non-symmetrical. Just going to put non-sim. I think we're getting the idea. And if it's non-symmetrical, the dipoles do not cancel. And if they don't cancel, then we've got a little bit of a dipole left. Then, yes, it's a polar molecule. All right? Sorry for that scribble at the end of the molecule. By the way, this is what my notes looked like when I wrote on the board before I had PowerPoints and things. So you just be thankful that I have technology, or it would be scribbles like this. It's just the way that works. Let's try to do an example or two, and then I will be done. Now, trust me, the note that was on there before was more complicated than this. This has actually been simplified. So hopefully you're still with me. Hopefully you're still kind of following along. Let's do some examples here, and let's do F2, all right, and then we'll do we've done a lot of these already, but actually I'll do it anyway. Let's do HF, and then we'll do a CBr4 and a PH3, and then I actually want to do one more, and I'll move the stuff down. So, how do we analyze these? Draw a Lewis structure to begin with. F2, and I'll use a different color just because I drew that in there. So F2, F 1 2 3 4 5 6 7 8. What's the delta En going to be for this? What's the delta En going to be for this? Maggie? 0. Delta En is 0. What does that tell me about that bond, Maggie?
That
There is no.
ugly dipole.
What did you say? There's no dipoles?
Yeah.
Oh, I thought she said ugly dipoles. I thought you said something in between there. There's no ugly dipoles. You're right. There's no dipoles in there. We don't have to worry about anything else at this point. What's this molecule going to be? Non-polar. So, right away we can go non-polar molecule. We're done. That one's done. That was easy. HF. Notice I don't draw any arrows. I don't put anything on that thing because it's non-polar. HF, we've done that calculation. Again, I'm going to write the delta En out completely on this one. Oh, sorry, that's not what I wanted to do. Is there a go back? Is there a go back? It's up here, isn't it? Ooh, nice. Oh, why does it do that? And 2.2 minus. I struggle with it. 3.98. 3.98. Do we have a delta? 1.78. 78. What's true about this bond? Yep. It's actually ionic. It's ionic. It's a little goofy. They're two nonmetals, but it exists in the ionic realm. We're going to still draw it. It's super polar, isn't it? It's really polar. Actually, you know what? Ionic. We'll stop right there. It's ionic. Yeah, we'll stop there on that one. That's ionic. I didn't even mean to do that. That messed me up. Let's do a CBr4. CBr4. Br, 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 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, delta En. Have we done a CBr bond in our work today? I don't know. Doesn't matter. What are the numbers? We can do it from scratch. Carbon. Two, 2.55. 2.55 minus 2.96. 2.96. So what do we got for a delta? Yep.
0.41.
0.41. So what's true about the bonds? They exist in the 0.4, or in that range. What type of bond is it? It's polar bond. Polar bond. We can put the arrows on here. What direction will the arrows be pointing? What direction will the arrows be pointing, Tim? Because it has the bigger delta En. So they're going to be pointing out that way. All right. Or we could have put delta negative, delta negative, delta negative, delta negative, and a delta positive on that carbon. Are there lone pairs on the central atom? No lone pairs. Oh my goodness. No lone pairs on. So let's just go with no lone pairs. Therefore, what's true about the symmetry if there's no lone pairs? If there's no lone pairs, it's symmetrical. Symmetrical. If it's symmetrical, what do the dipoles do? They cancel out. The dipoles cancel. And therefore, what kind of a molecule is it? Pardon? Pardon? Oh, you're right, it is nonpolar. I was thinking it was polar. That's why I kept doing that. I don't know. I'm looking at the time. Sorry. I usually get all goofy when I get tight to the time there. Nonpolar, she said it 3 times. Woo! I changed my mind. I don't want to do pH 3. So that's good. I'm trying to give you one. That's what I'm doing. I'm looking at the time. I'm struggling, man. Give me a break. CH2 Cl2. CH2 Cl2. CH2 Cl2. And you know what I got to do? I got to find your homework. The homework's on Google Classroom. You can find the homework on Google Classroom. No, there's nothing to be handed in on this. This is just practice problems. That's tomorrow's. That's tomorrow's. You can actually start that assignment because you'll be able to do everything except the last column. You're recording this? Be nice, Mr. Sanders. All right. C, H, L, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. The time is getting tight, so I'm going to just kind of go through this kind of quickly, but we actually have 2 delta ENs. We have a delta EN for C and H, and we have a delta EN for C and Cl. And I think we have those numbers hanging around. No, if someone could just tell me them, I don't want to write down all those little numbers. We're getting close for time. Do you have a CH number, Peter?
0.35.
0.35. And how about a CCl? Yep. 0.61. Notice what's true about both of these bonds. Yep. They're both polar. Polar. But notice that they're different sizes. Polar bonds. So we're going to check for symmetry. What can we say about the symmetry? What can we say about the symmetry? Are there any lone pairs? On the central atom? No. But are there different atoms connected to the central atom? Yes. So due to different atoms, different atoms, therefore it's not symmetrical, non-symmetrical, and therefore the dipoles don't cancel out. All right? In actual fact, these arrows point in to the C and out to the Cl. And therefore, dipoles do not cancel. Dipoles do not cancel. Therefore, this is a polar molecule. All right. That took a little longer than I expected, but I think we accomplished it. In terms of the practice problems, there are textbook problems that are on Google Classroom for today's date, Tuesday. I have already posted Wednesdays. The reason for that is there's another assignment that I want you to do to draw them up and tell me whether they're polar or not. The last column on this assignment that I'm going to give you tomorrow is the only thing you don't know how to do at this point. You could actually complete pretty well all of that assignment tonight if you wanted to work on it, except the last column. I need to finish off a lesson tomorrow for you to do the last column. It is not due, it's going to be due in a handful of days, so, well, not a handful, but it's going to be due in a bit. So you don't have to work on it tonight if you don't want, but you could. You could work on that tonight. You'd be able to do most of it. Okay, now I got to stop recording here for a minute.
Thank you so much, Mr. Singh. Great work today.